Hello everyone, welcome to Computer Logic Design lecture number 8, which we are going to talk about Karnaugh map. And let's see what is a Karnaugh map. Karnaugh map is an array of cells, or it's like a table, or like an array of some cells which it's consisting of some rows and columns, and those values which are presented in the truth table can be inside the Karnaugh map, and it provides a better way to simplify, or a quicker way to simplify, the Boolean algebra expressions. And Karnaugh map can be used for expression with 2, 3, 4, and 5 variables. If you have two variables inside an expression, we can easily use Karnaugh map, and 3 and 4. And the number of the cells inside the Karnaugh map is depending on the number of the inputs in the expression. For example, this is a cell, this is another cell, this is another cell. All together can be a Karnaugh map. And this is a cell, another cell, another cell, and all of them together can be called a Karnaugh map. Okay, and here we are going to write down the variable names, or the letters of the variables, which we are going to use in the next upcoming slides. And just know that this is a Karnaugh map, which is an array of cells, and each cell is going to have a value which is going to be 0 or 1. So the number of the cells is going to be 2 to power number of the inputs. If you have 3 inputs, the expression is going to be 2 to power 3, which is going to be 8 cells. If you have got, for example, which is here, if you've got 4 inputs, it's going to be 2 to power 4, which is going to be 16. 4, 8, 12, 16. So this is how you can find out how many cells do we have in each Karnaugh map. So for 3 variables Karnaugh map, you will be having 8 cells. The variables are going to be A, B, and C. So the A and B can be put together in one side, and the C can be in the other side. Let's see the other example. Look, here we've got A, B, and we've got C. We've got 3 inputs. 2 to the power 3 is going to be 8. 2, 4, 6, 8. And how we can write down the values here. For example, C is only one variable, whether it contains 0 or 1. It's going to be 0 or 1. However, A and B are 2 variables, and they can be, this 0 belongs to B and that 0 belongs to A. So it's going to be 0, 0, 0, 1, 1, 1, 1, 0. This is not a normal binary sequence. It's going to be called gray code representation. So what does the gray code say? It says first start from 0, 0, and start for the next one, start from the rightmost bit, the least significant bit, and change it. So the difference between this one and that one must be only 1 bit. So how many bits are different from those two and those two? There are only 1 difference. This bit is 1 here and it's 0 there. How about this one between that one? This one is 1 and that one and that one. This one is 0, this one is 1. So there is only 1 differences. And between that one and that one, only this bit is going to be different. In the normal ways, instead of those 2 ones, we are putting this 1 0 here, because this is 0, 1, and 2, and 3. So, but if we put 1 0 instead of those ones, what is going to happen? This is 1, this is 0, this is 0, this is 1. That means 2 bits are different from each other, and it doesn't follow the gray code rules. So in the gray code rules, we say the adjacent values of the adjacent status must have only 1 bit in difference. So this is applied. This can be applied on the what is called the gray code representation. So what is going to be here? 0 for A, 0 for B, 0 for C. 0 for A, 0 for B, 1 for C, which is going to be here. A complement, B complement, C complement. A complement, B complement, C. How about this value? 1 for A, 1 for B, 1 for C, which is going to be here. So it's going to be A, B, C. Here, 1 for A, 0 for B, 1 for C, which is going to be A, B complement, C. So how about 16? How about 16 cells, or how about 4 bits or 4 inputs in each Boolean expression? So the number of the inputs are going to be 4, A, B, C, and D, and 2 to the power 4 is going to be 16 cells. So A and B can be put together, and C and D can be put together. Let's see what's going to be here. 0, 0, 0, 1, 1, 1, 1, 0 for A, B. 0, 0, 0, 1, 1, 1, 1, 0 for C, D. As we said before, this follows the gray code rule. So inside here, what do we have? 0 for A, 1 for B here, and 1 for C, 1 for D. which is going to be S. So it's going to be A complement B, C, D. A complement B, C, D. Cell adjacency. So what do you mean by cell adjacency? So we see that in the Karnaugh map, all cells are arranged together in an ordered way based on gray code. So the cell adjacency means this cell is adjacent or neighbor with each cell, with that one, with that one, and that one. So let's see in a detailed way. For example, we have three variables Karnaugh map. These are A and B, and this one is C. So this cell is adjacent with that one, and it's adjacent with that one. And this cell is adjacent with that one, and that one, and that one. And even this cell is going to be rolled back with that one, so they are going to be considered as adjacent to each other. When you have a paper and you roll a paper, you roll the top of the paper to the bottom, so they are going to be adjacent. So we are considering this one as adjacent of that one, and that one, and this one as well. And this one with that one, and with that one, and even with that one. But they are not going to be adjacent diagonally. So that means this one is not adjacent with that one. Let's take this example. This cell is adjacent with that one, and that one, and that one, and that one. How about this one? Is this adjacent with that one, and with that one, and with that one? And the fourth one is going to be adjacent with this one. So like this arrow, which goes behind the Karnaugh map. So when you roll the paper, the right of the paper to the left of the paper, those two are going to be adjacent. And even that one is adjacent with this one. And that one is adjacent with that one as well, with this one and that one. And this one is adjacent with this one, and that one, and that one, and that one. So in three variables Karnaugh map, the cell is adjacent with three more other cells. This one, and that one. But in the four variable Karnaugh map, the cell is adjacent with four other cells. So that means this cell is adjacent with that one, and that one, and that one, and even that one in the other side. So when we have a gray code, 0, 0, 0, 0, 1, 1, 1, 1, 0, those which are belonging to A and B, and these 0 and 1 are belonging to C. So ones are read as the true variable, and zeros are read as the complemented variable. That means 0 and 0, which are zeros, are going to be read as the complemented corresponding variable. So this one is going to be A complement, and this one is going to be B complement. This one, A complement, B. A, B. A, B complement. C complement, C. So how about this example? In this example, we say, so before going to the example, let's say how we can eliminate the Karnaugh map, or how can we simplify the Karnaugh map. First, we look for the ones inside the cells, okay? So whatever we don't have, that means it's 0, okay? We look for the ones. So firstly, we look for the group of 8 ones which are adjacent to each other, okay? So that means we can take the groups in square shapes or rectangular shapes. So do we have any group of 8 ones together? No. So those are zeros. Do we have a group of ones together, a group of 4 ones together? No, we have only 3 ones. Do we have a group of 2? That means we can't take the group of 7 ones, 6 ones, or what's called 5 ones, and so on. We can't take the group of 3 ones as well. So in this Karnaugh map, we have those 2 which are adjacent to each other. Look, we can't take them directly together, those 2 ones, because they are diagonally adjacent, which we don't take them into account. So we can take those 2 together, and this one is going to be remaining alone. So when it's alone, we look for its adjacents. Are there any other one? Yes. So we can take it as another group as well. So this one is participating in that group and in that group as well. So this is how you can take the groups. So in order to simplify the total Karnaugh map, what we can do in this group, what is that variable which is participated with itself and its complement? Look, in this group, which variable has participated with itself and its complement? Look, A has participated with A complement and A complement. So A hasn't participated with plain A and the complemented A. Look at the B. B has participated with B complement and B. And C has participated only with C complement. And we say that those variables which has participated with themselves and their complements are going to be removed. So the B is going to be removed. How? So A, what do we have here? A complement in that group. We are writing down a complement. And for this one, the B has participated with itself and its complement. So the B is going to be removed. And C has participated only with C complement. So it's going to be A complement, C complement, A complement, C complement. How about the other group? This group, A has participated with A complement and B has participated with B. How about C? C has participated with C complement and C. So we are going to remove the C. And what do we have? A complement B. A complement B. This is how you can analyze, or how can you simplify a Boolean expression within Karnaugh map. Okay, let's take this example. We have 4 inputs Karnaugh map. That means we have 16 cells, and those bits are ones and the remaining bits are zeros. First, we look for 16 ones together. Do we have them? No. Then we look for 8 ones together. Yes, we have, but they are not they are not adjacent to each other. For example, this one is not adjacent with that one. That one is not with that one. So we can't take a group of 8 ones together. Then we look for a group of 8 ones together, 4 ones together. This is and that one. They are all adjacent to each other, so we can take them as a group. And the next one, those 2 are together, but they are adjacent with those 2, so we can take that group and that one and that one. So both of them are going to be grouped together. So a group of 4 ones is better than a group of 2 ones. So it can give us a better simplification than group of 2. So we can take those as a group of 2, but it's wrong because a group, first we look for a larger group. So let's analyze it. In this group, what is participated? A complement, B complement, and A complement B. So what is going to be removed here? B is going to be removed. So what's going to be the result? A complement, and the upper side is going to be C has participated in C complement and C. However, the D has participated in D complement and D complement. So the B here and the C here are going to be removed, and the result is going to be A complement and D complement. So the upper yellow group is read as A complement, D complement. How about this group? A hasn't changed. A has participated with only itself, A. And the B has participated with 1 and 0. So the B is going to be removed. How about the upper side? The C has participated with C complement and C. So it's going to be removed. However, the D has participated only with D and D. So the D is going to be removed. So the result is going to be A and D. So the result is going to be A and D. So the final value is going to be A complement, D complement plus AD, which gives us the sum of product expression. And in another way, we can easily get the standard sum of product expression using the Karnaugh map. Let's take this example. We have this one, that one, that one, that one. How to get the standard sum of product expression? We just take the ones into account. This one is A complement, B complement, C complement. This one is A complement, B complement, C, which is this one. And that one is that, and that one is that. So you can easily get the standard sum of product expression using having the Karnaugh map. How about this one? So it is vice versa. We can just easily, give the map the standard sum of product expression into the Karnaugh map. So what is here? A complement, B complement, C, D. For the A and B, we take the zeros into account, and for C and D, we take the ones into account. So A complement, B complement, C, D, which is here, is going to be 1. So whatever any product term we have, it's going to be 1 inside the Karnaugh map. And for that one, for example, A, B, C complement, D complement. This is A, B, and this is C complement, D complement, which is going to be this cell. It's going to be 1. That one. For example, that one. A, B complement, C, D complement. Where is A, B complement? Here. A, B complement. And where is C, D complement? C, D complement, which is here. So they are going to be this cell, which is going to be 1. A, B complement, C, D complement. This is how you can map a standard sum of product expression into a Karnaugh map. And how to map non-standard sum of product expression. First, we need to change them, or you need to get the standard form of that non-standard, and then we can put it inside the Karnaugh map. Let's say we have this example: A complement, AB complement, ABC complement. So the AB complement, lacks of C. The C is missing there. So one time the C is going to be 0, and the same time the C is going to be 1. So it's going to be AB complement C and AB complement C complement. Here is missing B and C as well. So it's going to be A complement, B complement, C complement, B complement C, BC complement, BC. So then this is going to be the standard. So that means how many ones do we have inside the cell? 1, 2, 3, 4, 5, 6, 7. That means we have 7 ones inside the cells of the Karnaugh map. These are some examples here, and that one, how we can group them together. In this one, we can take those two together and those two together, and this one is going to be remain alone. Is it adjacent with that one? No. Is this one is 0, 1? No. This one is not 1. And we can take it with that one there, but there is no one there, so it's 0. So it's going to be taken alone. So this one is going to be alone. How about those? Those two together and those 4 together, and this one can be grouped with that one, and that one is grouped with that one. Here, as we said, we can take the groups rather in rectangular shape or in square shape. Those 4 together and those 4 together and those 2 together. If you have another one there, we could take them as a group of 4. Here, those 4 ones and those 4 ones, they are adjacent with each other. If you roll the right side to the left side, so you can make a group of 8 cells, and those 2 are going to be remaining, so you can take them with those. So any one can be grouped more than once, and that one is going to be remaining alone. It's going to be taken, or it's going to be grouped with, it is adjacent, so it makes a group of 2. As we say, a larger group is better than a smaller group. So how to determine the minimum sum of product expression? Look, in this group, which is a group of 4 in that group, so what are the variables participated? A complement, B complement, B. So the B is going to be removed. What's going to be remaining? A complement. How about the upper side? C, D complement, D complement. So the D is going to be removed. So the variables remaining there is going to be A complement and C. How about this group? A complement, A complement, A, B. So the A is going to be removed, B is going to be there. How about the upper side? So look, we take the whole horizontal values into account. So C complement, C. So the C is going to be removed. D complement, D. So the D is going to be removed. So what's going to be there? Only B. How about this group? In this side, A has participated with only A. However, the B has participated with B and B complement. So the B is going to be removed. And what is going to be remaining? A, which is that one. How about the other side? C and D has participated with C complement and D. Are there any C or are there any D complement? No. So what is there? C complement and D. And here are the solution of the other examples, so you can just find out easily. So in this example, it asks us to use the Karnaugh map to minimize the following standard sum of product expression. So the standard form is that one. So we can take each one, A, B complement, C. A, B complement, C, which is here. So we can write down one there. A complement, B, C. A complement B, C, which is that one. So we have 5 ones and we have 5 ones there. And when we've done that, we are going to group them together. Can we get a group of 8 ones? No, because there are not 8 ones. Can we get a group of 4 ones? Let's have a look. Those 2 and those 2 are adjacent to each other. So we can take them as a group of 4. And this one is going to be remaining alone. So it's adjacent with that one. And as we said before, each one can be grouped more than one time. So we can take it as a group of 2, and then we are going to minimize them easily based on those rules which we just discussed. And this is another example. We have those 4 variables Boolean expression or sum of product expression. This is not standard. We are going to change it to standard, which is going to be A, B complement, C complement, D complement, A complement, B complement, C complement, D complement. And they are going to be put inside the Karnaugh map, and we will get this one. And those 4 and those 4 are going to be grouped as an 8 ones, and those 2 and those 2 are can be grouped with a group of 4 ones. And the final result is going to be D complement or B complement C. And other ways we can easily map directly from a truth table. We have this truth table and we take only the ones into the Karnaugh map. So this is 1. So what are the inputs? A complement, B complement, C complement. A complement, B complement, C complement, which is here. And that one is A, B complement, C complement. Where is that one? Which is going to be this one. A, B complement, C complement. A, B complement, C complement. And that one, A, B, C complement, A, B, C complement, and A, B, C, which is this one, A, B, C, and it's going to be 1. So how to group them together? Those two are adjacent to each other. If we want to simplify them using Karnaugh map, we take those two together, and this one is adjacent with that one. So we are going to take them together. We could do that, but there is another one there which is adjacent with that one, so we can easily take it with the other one, not that one. We can take a 1 in more than one group if we need, but in this case we don't need to group it with this one. Okay, this one can be easily grouped with that one. And there is something else. For example, if we map this truth table into the Karnaugh map, which is called don't care case. Look, for those inputs we have 0, for those inputs we have 1, but for those inputs we have something else which say we don't care whether it is 0 or 1. Okay, so we don't need them. But when we map them into the Karnaugh map, we map them as X. X means don't care. And that don't care may be 0 or maybe 1, which we don't need. But in order to simplify our Karnaugh map a better, or we can more simplify it, we can make it to its simplest form, we are going to exploit those don't cares as 1. So we are going to use them as 1. So they are going to be grouped together. And that one with that X is going to be grouped together. So if you use the X's, or we don't take the don't cares into account, those two are going to be grouped together because we have only 3 ones. So this one, that one, and that one, if we map them to the truth table. So those two are going to be grouped together, and that one is going to be grouped alone because there is no adjacent one next to it. So the result is going to be A complement B C D, and this one A B complement C complement. So without don't care, we will get this sum of product expression. How about with don't care? With don't care, we exploit the X's into 1. So those 8s are going to be grouped together, and the result is going to be only A. And that one is going to be grouped with that one as a group of 2. So the result is going to be B, C, D. So the result is going to be A or B, C, D. So this one is simpler than that one. So that's why we exploited the don't care cases into 1. So let's move to the product of sum. As we said before, the product of sum is the opposite of the sum of product. If you have this product of sum expression, which is A or B or C, we consider them as 0 when we are talking about the product of sum. And what is going to be inside the Karnaugh map? This 0 is going to be there. And this one, A, which is 0, B complement, which is 1, C is going to be 0 because we are talking about the product of sum. So 0 is going to be in that place. And for that one and that one as well. And we are going to group the zeros together, and the remaining parts are going to be 1. We don't take the ones into account when we are talking about the product of sum. So how about this example, which is product of sum expression? A complement B complement C D. 1 1 0 0 1 1 0 0, which is going to be here, and we put 0 here. A complement B C complement D complement 1 0 1 1 1 0 1 1, which is here, and the remaining for the others. As we said, we have written this one there, and you can easily map them to the Karnaugh map, and then put 0. We put 0 for those cells which belong to any sum product in the product of sum expression. So the rule of the grouping of zeros are the same of the rule of grouping of ones. If you have this one, so the values inside the Karnaugh map are going to be those. Those cells are containing zeros, and those cells are containing ones. So you can get those 4 zeros together and then simplify it, which is going to be A. And that one is going to be, so in this group, what is going to be changed? A is changed, right? 0 and 1. So what's going to be remaining? B. So, but in here, which we are talking about the product of sum, we have 1, so we take the B complement because we have product of sum. And here we have 0, which C hasn't participated with 1, with 0 only. So when it is 0, we just write down C, and we are talking about the product of sum. And then we just, instead of writing down B complement C, we write down B complement or C. However, for the sum of product, we could just refer back to the previous method, which we were talking about, the sum of product. Here, B has participated with B and B complement, so you remove the B. A is only B remaining there, and the C has participated with only C, so it's going to be AC. And for that group as well, we come back to the sum of product. However, for the product of sum, is going to be, everything is going to be different. So this is the last example. We use Karnaugh map to minimize the following product of sum expression. So is it standard? No, this one is missing A, so we can say A or B or C or D, and A complement or B or C or D, as we have here. A complement or B or C or D, A or B or C or D, and then they are going to be put inside the Karnaugh map as 0. So this one is A complement B C D, that means 1 0 0 0. So where is it? 1 0 0 0 here. And that one, A B C D, which is going to be 0 0 0 0 0 0 0 0. And that one, A B C complement D, 0 0 1 0 0 0 1 0 0 0 1 0. So it's going to be 0. And then when we finish that, when we complete that, we are taking the groups. Those 4 are adjacent to each other, so they are going to be in one group, and that one is alone, but it is adjacent with that one, so we can take it as a group. And this one is alone, we can take it with that one as a group. And the remaining, so the result is going to be a product of some expression. So what is changed there? C has participated with C complement and C, so it's going to be removed. The result is going to be A or B or D, because they are all zeros. We are talking about the product of some. And this one, what is missing? A has participated with 0 0 1 1, so the A is going to be removed. B has participated with 0 and 1, so the B is going to be removed. So C has participated with only 0 and D with only 0, so it's going to be C or D, and for that one as well.